Let's go ahead and curve sketch this rational function and see how it turns out. Since this is a rational function, the domain is going to be all real numbers except for when the denominator is 0. The denominator is 0 when x is equal to 7. Therefore, the domain is all real numbers except when x is equal to 7. Also, if you plug in 7, you don't get a 0 on the top. And that shows that 7 is going to be a vertical asymptote. We get a vertical asymptote when x is equal to 7. If we want to look at this a little bit more in depth, right now we could say, well, what's going to happen as x approaches 7 from above and when x approaches 7 from below? So as x goes to 7 from above, my function h goes to, well, if we're above 7, then something a little bit above 7 minus 7 will be positive. We also have positive, so we go positive over positive. We're getting a positive infinity. So the limit as x approaches 7 of the function h of x is positive infinity. This is just another way to write limit is positive infinity as x approaches 7 from above. As x approaches 7 from below, my function h of x approaches, well, the denominator is going to be a negative. This is going to be a positive. So positive divided by negative becomes a negative, and it turns out we get negative infinity. So that's how that vertical asymptote works. Now let's take a look at finding the critical values and critical points. We're going to do that by utilizing the first and second derivative. In order to take the first derivative, I'm going to use the quotient rule, which says take the denominator and square it. The numerator becomes derivative of the numerator, that's 3, times the normal denominator minus normal numerator multiplied times the derivative of the denominator. This can be simplified 3x minus 21 minus 3x minus 6 and then we can combine like terms, this minus 3x and that minus 3x cancel each other out. We just get negative 27 divided by x minus 7 squared. Now this derivative cannot exist. There's a spot where it doesn't exist. That's when x is equal to 7. But we kind of already know that's what the vertical asymptote does. So what about this derivative being 0? Well, this derivative can't be 0 because the numerator can never be 0. So if you look at this numerator, you can never achieve 0 in the numerator. So we have no critical values because the derivative, when it doesn't exist, that's already where the asymptote is. And where the derivative would be equal to 0 can't happen. So there's no equal to 0. Not existing happens at the asymptote. Therefore, there's no critical values, no critical points. Let's look at the concavity by looking at the second derivative. I'm once again going to utilize the quotient rule. So I'm going to take the denominator and square it. If I square an x minus 7 squared, I get an x minus 7 to the 4th power. And then we look at quotient rule derivative. Derivative of the numerator would be 0 times my normal denominator minus normal numerator multiplied times the derivative of the denominator. The derivative of the denominator, we have to use a chain rule. So 2 multiplied by x minus 7 to the 1st power times the derivative of the inside function. Well, the derivative of the inside function is just 1. 1 times anything is itself. If I clean that up, 0 times anything goes away. Negative times negative 27 times 2 is a positive 54 multiplied times x minus 7. If you want to simplify that, there's a factor of x minus 7 on top that can cancel out with one of the factors of x minus 7 on the bottom. Notice that when this doesn't exist, once again, it happens at the vertical asymptote. Is there any way that this could be 0? No, there's no way this could be 0. So there's also no points of inflection with this example. So essentially, the asymptote is giving me the whole entirety of what the graph is doing up and down and how the critical values, or excuse me, how the concavity of the graph is going. Might be different to the left of 7 and to the right of 7, but that's how it goes. The other thing we should do is look at the behavior of this graph as x goes to infinity. We take this graph and we say as x goes to positive infinity, we'll plug in a really big positive number. It turns out if you take the limit as x goes to positive infinity, this function goes to 3. If I plug in a really big negative number, and you look at what's happening as x gets bigger and bigger and bigger, in the negative direction, it turns out that the function also goes to 3. I just didn't want to write limit as x goes to infinity is 3, and then limit as x goes to negative infinity is 3. So that's what that is. Now I know how to graph this. I know the behavior as x goes to infinity. I know the points of inflection. I know the critical values. I know the vertical asymptotes and what the graph's doing at those vertical asymptotes. Let's go ahead and graph this. So the vertical asymptote, x equals 7, is right there. Let me change that. I've been writing those in green, so asymptotes in green. There's no critical values or critical points. There is a horizontal asymptote of y equals 3. And what we know is that as x goes to 7 from above, it goes off to positive infinity. If I'm going to write that, maybe I should keep closer to the, it's going to look like something like that. And as x goes to infinity, we're going to go out towards 3. So something like this. I don't know how close we get to the actual asymptotes and how quickly that happens. But the reverse is true on the other side. We're approaching 3 as we go out towards infinity. And then as you approach 7, you go down to negative infinity. By the way, it's a good practice to look at the concavity here. Obviously, we can see it as we graphed it, but the concavities are going to be different on the left-hand side and on the right-hand side of the asymptote. That's a good little thing to look at. But here, I'll do that algebraically in just a moment. But you can see what's happening as we do this. So we got the second derivative, but what I was trying to say is concavity to the left of 7 can be found out by just plugging in some number that's less than 7. Let's plug in 0 into the function. That would be 54 over negative 7 cubed. The important part there is that that's a negative, and so we're concave down to the left of 7. We saw that graphically. And then to the right of 7, we just need to plug in some number which is above 7 into our function. Plug in 8, for instance. 54 divided by, well, 8 minus 7 is 1, so you got 1 cubed. So 54 over 1 cubed. The important part of that is that it's positive, so we know it's concave up when you go to the right of 7. This also shows that concave down and concave up don't always have to have that parabola shape when we come back up. In other words, the concavity was up, but this function never actually turned back up like a parabola did. This was still concave up the whole time. It's slowing down, but it's slowing down and it's still approaching, or excuse me, it's the derivative is increasing, but it increases having a derivative whose limit is 0. Hopefully that makes sense. So it's increasing all the time, but it's increasing in a very, very, very slow way here, so that the derivative stays and becomes really close to 0. Same thing on the left of 7. This concave down. As you move towards the left, that doesn't mean you turn back down and always. So this on the right is concave up. This on the left is concave down. And we can't have concave down things have a limit. We can't have concave up things have a limit. If we look at the actual function of what we have, it is, what is that? 3x plus 6 divided by x minus 7. Oh, I was too close, I guess, to the actual things for this to work. So I should have had that. Let's highlight that in red. So the red is what I'm looking at. So I got the general concept right. Again, I'm not quite as, I was a little bit too close to the asymptotes too early this time. Last time I was a little bit too far away. And if you ever want to get more accurate, you can always, how far away are you at the asymptotes at this stage? You can just plug in some points. That's how to do curve sketching with these rational functions.